Thank you very much for invitation. I would say that probably, unfortunately, my talk was assigned to this panel uh, of quantum computing, but as you will see later on my slide, it has no so practical meaning like two previous talks. Yes, it's called quantum computing, sometimes quantum operations, but as you will see, it's not so close to practical realizations and applications. Sorry? Yeah, you're right, like usual. Yes. If I understood correctly.
On the other hand, show us practical quantum computing.
Yes. Yes. Yeah. Oh, yeah. Good. Good.
Don't be so shy.
So yeah. My aim is to to present something towards practical higher order quantum computing. Then. Good. So before I start, I would like to give credit to all my collaborators. Um, yes. Um, so this is what I'm going to talking about. So I focus on point from first to the fourth, and maybe after my talk we can discuss also more practical applications of higher order quantum operations. So let's start from the motivation. So I try to motivate it from the practical side. So this is the first slide. So we know that in classical computations, right, we operate on bits, on classical bits, so 0 and 1. And in principle, we have perfect control of that bits, right? So I don't assume any bit lost, anything, but in principle, right, from the point of view of theory. And in many practical applications, we want to manipulate some bit strings using some function, let's call it h, right? So we have some bit string on the input, we apply this function, and this function returns us another bit string or just one bit according to the input. But we can also go one level higher and try to design functions that manipulate on another functions, right? And the point is that the body of this function h can be partially or fully unknown, and we can ask what we can say about g, the function g that accepts this unknown functions h, and our goal is to basically design this g in such a way that it's somehow universal. So whatever h is, this function g always prepares the same operation on this unknown function. Unfortunately, in quantum case, we don't have this notion of perfect manipulation, because we know that there is, for example, non-cloning theorem that having unknown quantum state, we cannot design operation that produces perfect clone, and classical bits we can copy, right? There is impossibility of gate replication, so let's say gate cloning, and also impossibility of perfect iterating of unknown quantum gates. But in some cases, when we have access to multiple copies of an unknown state, we can a little bit cheat and increase the performance of our task. So here I've chosen very old result by Werner, saying that if we have if you want to copy unknown states and we have many many copies of the input states to copy, then we can a little bit increase the fidelity, or at least we can observe how it changes between number of inputs and number of outputs. And our goal is the following, that we assume that we have some abstract device, and on this abstract device we encoded, let's say, some quantum process with some command G. And this command G accepts k copies of unknown unitary. So this is so it can be considered as a supermap, and this supermap G is designed in such a way that it accepts this k copies of unknown program U and produce, for example, single copy of U dagger, U transpose, or U conjugate. So this is complex conjugation. So today I will focus on this case, the simplest one, and we will try to find the scheme that allows us to prepare this single copy of complex conjugation of unknown program U as good as possible. But to say something more about that, we need to introduce a few classical notions from theory of quantum channels. First is a relation between quantum linear maps and so-called Choi-Yamiokowski operators. So basically, there is one-to-one correspondence between linear maps. Linear maps will be denoted by tilde and so-called Choi-Yamiokowski operators. And this isomorphism is given by the action of the linear map on the half of the maximally entangled state, here unnormalized. And why is it important? Because then investigating properties of our linear map can be translated on investigating properties of the corresponding matrix. So we can say that our linear map is completely positive CP if and only if this matrix is non-negative. So all eigenvalues are non-negative. Also, we can say that our map is trace preserving in and only if and only if when we trace out the matrix C over outputs, we obtain the identity operator. And just to fix some notation, we can introduce unitary linear maps and corresponding Choi vectors also in the similar notion like here. Good. So now when we have access to few linear maps, we can compose them, right? So suppose that linear map acts from H1 to H2 and B from H2 to H3, then we can write the third map, which is composition of these two. But we can ask how to translate this composition on the level of Choi-Yamiokowski operators. And there is also one-to-one translation given by Chiribella, and it's called link product. So the Choi operator of the composition of two maps is given by the following formula involving Choi operators of maps A and B. Good. So now last definition that we need to introduce here, it's called quantum comp or incomplete quantum circuit. So basically we consider super map, that in other words map that accepts other map, right? That map that can manipulate on other maps, and it's called incomplete because here in general we have empty slot, and this empty slot is for inserting unknown quantum channels or quantum gates that we want to manipulate by our supermap S. And it was shown that every such single slot quantum comp can be represented as a encoder, decoder, and some auxiliary space, right? So all these compositions here can be written in terms of link product introduced earlier. Good, but that was for single slot, but in general we can have quantum comps that accept k copies of unknown channel C. And then there is a question how to order the inputs. So we have three cases. Here I'm gonna talking about only about two, the most, let's say, practical one. So the first possible ordering is parallel one, where we use all k copies of C at the same time. And to ensure that this guy, A, auxiliary space, and D is indeed quantum comp, we have to satisfy a bunch of constraints. First of all, S, so the composition E of D by link product must be positive, and also we need to satisfy these trace rules. In the sequential configuration, right, we have many encoders and one decoder. Here I focus only on the case when we have access to two copies, because then it's easy to write the constraints that this super channel must satisfy. When we increase number of slots, of course, here we have a lot of more constraints. So it means that at least from the point of view of theoretical investigation, sequential order is much more complicated than parallel one. There is also the third one that attracted recently quite, well, I would say a lot of attention. It's called the indefinite causal order, where we don't have, let's say, time ordering, but it's even hard to represent it graphically, so I don't have it. But the most important case is that the most efficient, what does mean efficient, I will define later, but in general, the most efficient quantum comp is this indefinite one, and the less efficient is, in general, parallel one, right? And the sequential one is somewhere in between. But this is not always the case. For example, for the case that we want to talk about today, so when from k copies of unknown unitary program we want to obtain a single copy of U bar, it was proven that sequential strategies and indefinite causal strategies cannot perform parallel ones. It means that this strategy gives you the same quality of the output as sequential or indefinite. And this is really good for us because then we have easiest constraint to deal with. Good. So our goal now is to find the optimal decomposition of S in terms of encoder and decoder to obtain a good simulation of single conjugation of unknown unitary gate U. So I've been talking about the quality and what we mean by quality. Basically, by quality, we mean the fidelity between channels. So, U tilde is a perfect realization of our output. In our case, this is U conjugation, and C tilde, this is super channel that simulate this process of conjugation. And we ask how close are they? And the fidelity between these two quantum channels translates into the following relation that involves traces of respective Choi-Jamiukowski states of these two channels. Good. And our goal is to find this expression analytically. Just maybe some remark. So in our case, we consider deterministic non-exact scenarios. So in principle, we expect that this fidelity can be lower than 1. And we ask what is the dependence between the local dimension, number of copies involved, And is it possible to reach, for example, fidelity equal to 1 when we increase number of copies? There are also probabilistic exact transformation, but I'm not gonna talking about them during this talk. So formally, we should ask about the fidelity in the worst case scenario, right? So basically, here is our function. Here is our idealized output, right? So our G accepts k copies of U and produces single U bar. And here's our simulation. So our quantum comp accepts k copy of U and produces U bar, which should be relatively close to this guy, right? And we want to find U that minimize this fidelity here. And then it is called the worst case scenario. On the other hand, we could have the simplest approach, namely we could ask about average fidelity. Then we simply average this expression over the whole unitary group. And basically, there is a theorem saying that when function G is homomorphism, so it acts like this, or anti-homomorphism, so the order of action is reversed, then this worst case scenario, this worst case fidelity equals to average case. And here, yes?
There, the composition, is it in terms of channels or in terms of unitaries? Just the matrices.
Here is of unitaries.
So it's not a. So it's like those are just unitary channels.
Yes.
Okay.
Okay, and as you expect, when we involve only one copy for our function G, so here if we put k equal 1, the average fidelities are not really high, right? So the question is, can we do better when we increase number of inputs? And to do so, people introduce so-called performance operator. It has some theoretical inspiration. There is some theoretical inspiration behind this, but here I'm just using it only from the technical point of view, because it can be shown that this average fidelity can be just is just a trace between this performance operator and this quantum comp that accepts k copies of unknown program U. And the task, we want to find this S, which gives the best average fidelity. It's important to notice that we cannot just put S equals to omega, because we have to also satisfy a bunch of these constraints from the previous slides, okay? And so this is the trick. But careful analysis of this problem shows that performance operator satisfy a bunch of properties, namely it commutes with the following unitary actions on different sites. And this allows us to write it as a linear combination of projectors that span the following commutant between diagonal action of unitary group. But basically, these projectors commute with diagonal action of unitary group. So in other words, using so-called sure while duality, they can be written as a linear combination of permutations. Okay. So theory of such commutator is well known, and these projectors then are also well known, and basically they span irreducible representation for permutation group of order k. This is some technical thing because every E-reps of symmetry group can be labeled by so-called Young diagrams, right? And from these Young diagrams, basically, we can add we can add or remove box, and this procedure represents so-called induce and reducing operation. But now we would like to somehow use these symmetries to find the fidelity. So, finding the optimal fidelity can be recast as a SDP problem. So basically, you want to maximize this value with respect to these constraints. Okay, and this, in principle, when we in principle, if we just guess the S without solving max, we'll get lower bound on F of F average. So we can also construct dual problem, which gives then upper bound on the average fidelity. So we were hope that having this, let's say, primal and dual problem plus symmetries coming from representation theory for symmetry group will be able to solve this max or min problem analytically. But it was not the case. Even with representation theory, it was really hard to explicitly solve one of these problems straightforwardly. So maybe I will skip. This is just okay. Good. So we decided to do the following. Instead of solving this maximum problem in the primal problem explicitly, we just chosen the feasible solution. We just postulated, oh, let's assume that S is the product form. So here we have encoder and decoder, and the form of encoder and decoder are the following. Okay, so A is just antisymmetric projector. Then, since we did not solve maximization problem explicitly, the primal we obtain only some lower bound for the real solution from the SDP. Good, and the lower bound is the following. Of course, this S satisfies all the constraints coming from SDP. That was the construction. Okay, so we have lower bound that involves number of copy and local dimension. And also, we're able to find some feasible solution for the dual problem. And the dual problem involves some heavy machinery from combinatorial representation theory for symmetry group. But the nice was, as you can see, that the upper bound for average fidelity is given by the same formula, right? So it means that the solution for the primal and dual problem coincide, right? So it means that instead of having some lower and upper bound, our lower and upper bound gives the real value of our optimization problem. Good. And since we have the same upper and lower bound, we can say that we have property which is called strong duality, and the average fidelity is given by this reasonably by very easy expression. And here we have plots for various dimensions, and we see that whenever k equals d minus 1, we can obtain average fidelity equal to 1. So what was interesting here, at least from my perspective, that we can play a lot with symmetries coming from, let's say, standard representation theory called Schur-Weyl duality. Using these symmetries and some smart guess, we could solve SDP analytically by imposing feasible solutions. We showed that auxiliary system is not needed. The optimal superchannel is a tensor product of encoder and decoder. And we show how the average fidelity depends in terms of number of involved copies. Of course, we have also other transformation, right? So For example, if you want to obtain dagger, it was shown in this paper that for qubits we need only four copies of U to get fidelity equal to 1. To obtain this result also, sure while duality is used. And the last thing is the transformation when you want to obtain a single U but transposed. So in this case, almost nothing is known in general, mostly due to more tricky symmetry, which involves, let's say, deformed diagonal action of unitary and partial transposition. So now we don't consider a symmetry group, but we consider permutations that are partially transposed with respect to some subset. But what is nice, I have no idea if it has practical implications or not, that at least some authors claim that there are efficient quantum circuits for such type of dualities like Schur-Wey duality and mixed Schur-Wey duality. So maybe potentially it will be possible to, I don't know, hook some interesting, at least from the theoretical point of view, quantum circuits for simulating these processes. And I think it's quite reasonable to think about this since we need only four copies, right? So I don't know.
Can you say again why k must be more equal to b minus 1?
Yes, this is technical assumption because at some point of the proof we use from orthogonality relation for irreducible characters. And basically, if you don't have this assumption, you cannot sum over the whole group and you cannot use Schur orthogonality relations.
So in this case, you cannot get the fidelity 1, right?
We can't. Yes. So I think that's all what I had. Yes, that is.
Thank you, Michał. So we have ample time for questions. So what's the G function for the complex conjugation of U in the case where the number of copies is d minus 1?
Okay, so G function. So this G function is this S, right? So the S is it has tensor product of encoder and decoder, and this E and D are the following form. Let me find it here, right? So this is encoder is just proportional to antisymmetric projector, and decoder is more complicated one.
But the fact that you have the fidelity equal 1, does it follow from the characteristic polynomial of the matrix for U or something?
I don't think so. I don't know. Well, this is just purely a result of SDP, right? By our guess.
Okay, more questions? You are in a second.
So if I understand correctly, you just have a machine which is purely deterministic. I feed you k copies of some unknown unitary, and you always can guarantee that I get a transpose of this. Or just
Correct.
okay, thanks.
No problem. No problem.
Okay, so would it be difficult to get again Neumann measurement in a basis given by you instead of just the unitary?
Probably yes.
How much will
Well,
change?
when you have measurements, probably you're gonna lose a lot of symmetries, right? I
Yeah,
think.
but basically you can think about it in just a rotation by you and measurement in a computational basis. Usually the results we get is some equivalence with diagonal unitary matrices.
I see.
As an equivalence class and then just optimize over all diagonal unitaries.
I see. Okay, so now I see that maybe there is some potential, right, to say something, but I can't say much about ad hoc right now. Okay.
There's more. Lucas, please.
I have a question about this mathematical fashion
Yes.
paper about like like combinatorial like aspects of this this
Yes.
representation theory. So can you just elaborate what's
Yes. Yes.
there?
Okay, because we postulated some feasible solution for dual problem, right? And we knew that it satisfies all the constraints, but when we put everything into expressions that we had, we obtain this maximization problem. And this m beta, m lambda are just multiplicities of the symmetry group, irreps of the symmetry group in the Schur-Weyl duality. And numerics showed us that this maximization, when you do it numerically, matches with this expression. But we couldn't find a close expression for that. And by some mistake, I found some Russian journal, Soviet. I'm sorry, Soviet. I couldn't
Surname sounds Ukrainian, actually. Pershik.
Okay, I know that this guy won Fields Medal, I think. So I couldn't understand much because I don't know Russian. I could understand only some symbols in this paper. But the combinatorial problem solved by this guy was really close to the combinatorial problem that we have. It was not the same, but we could build on these results. Yeah.
One more remark from there.
No, but just this is a very, very serious mathematician passed away last year. I met him in band level at the conference organized by Marek Bożejko from Wrocław, you might know, and Marek really esteems.
Yes.
Very, very.
Yes. He invented. Well, there is Vershik-Okunkov approach for symmetry group. Yes.
Now, before next question, since I had no opportunity to ask questions before, I will use the power of mic. I have a very naive question. What is the motivation of such a simple operation which sends k copies of an unknown unitary to just one copy of transpose, dagger, or complex conjugation? Why is that interesting? Because it sounds a little bit like wasting the resource. You have k copies of unitary and then you produce just one unitary, which is a transpose or complexly conjugated.
Well, I think the main motivation comes from the translation of classical computation when you have this computations of higher order, right? That you want to transform other functions, like you write some program in Mathematica, right? You have some modules, procedures, and then you can use these functions in another functions, right? So that was our main motivation. Is there any practical motivation? Is it worth to pay the price, having k copies of unknown unitary to get U dagger? I don't know. Maybe there are some cheaper way to obtain U dagger from k copies of unknown U. This I don't know.
Yeah, for me it sounds very similar to this error corrections idea that you have many copies. That you have the same circuit repeated, and you just make this in order to make correction. Yes, because if you have many copies, you then know how. If you, for example, make 3 copies and you have 2 results versus one different results, you decide that this more frequent result is better. Yes. So
yeah, maybe, but here you don't have to decide anything, right? You just fit, let's say, the comp, and you get the answer, and you have promised that the quality is 1.
Łukasz, and then
So maybe just a short comment for you, Jarek. If you want buzzwords, you can think of this as quantum machine learning, because you have a now operation to use now, store it, and use later. So you can say that you have some convertible operation.
Yeah, but here we don't store anything, right?
Well,
This is.
I still don't know what the view.
Well, you don't know it, but you can apply it.
Yes.
You can also apply.
Yes, but you cannot apply inversion.
You cannot.
Yeah.
Okay.
okay, now Emmy.
Very quick, following up on Jarek's question, how much harder would it be to implement not dagger, not Hermitian conjugate, but sort of a simple unitary operation like permutation of 2 columns, let's say? Doesn't make any sense, and it would be much harder.
This, I don't know, honestly speaking, right? Our motivation was completely different. So it was not motivated by what is hard, what is what is not. We didn't care honestly about practical motivation, right, to solve this problem. Our motivation was to check what are the limitations of quantum supermaps for transforming this the atomic ingredients of every quantum algorithm, right, which are unitaries. Yeah, so this I don't know.
Maybe it was mentioned.
Wait. I am the boss here. So there's one more question.
Do you have some lower bound on this K for all those operations? Like the optimal K, the minimal number of copies you have to feed to have fidelity 1? You probably mentioned that already.
Yes, so for the case of unitary conjugation, it depends on the number of, it depends on the local dimension. So when dimension of U is D, you need K equals D minus 1 copies to obtain average fidelity 1, right? For unitary inversion is, I don't want to say that it's dimension independent because we don't know, because the solution is known only for qubits, but for qubits we need only 4 copies to get average fidelity equal to 1. For this kind of transformation, we don't know. The conjecture is that you need D plus 2 copies to obtain fidelity 1.
Thank you. Any more questions? I have one. So you mentioned indefinite causal order.
Yes.
Did you play with that? Like, does it give any advantage? Does it make sense to use it?
Yes, there is a lot of sense. But as I said, from the indefinite causal order, in principle, we can obtain upper bound for the sequential, right? But why we care about this? Because as you remember, the sequential, the constraints for the sequential comp are quite complicated, right? Here we have only 2 uses, and already we have a bunch of constraints. So when we have K copies, we have more constraints. And when you apply indefinite causal, basically you reduce all these constraints to just 1.
Okay.
Yes.
Okay. So
but the bound, yes, but we don't have any promise that the bound is tight, right?
Okay.
Mhm.